Well, I'm sure we've all done this. We browse the internet for a product we want, a ticket or a DVD. We put in our credit card details, and just before sending them off, we pause and think, is this really safe? What if someone was to intercept the wireless network or the cable running down the street and steal my credit card details? Well, it is safe, and the reason it's safe is because of prime numbers. For centuries, mathematicians have been wrestling with prime numbers. Those in the red corner have been searching for larger and larger primes, while those in the blue corner have been looking for ways of breaking numbers down into their prime factors. In this professional knowledge programme for maths teachers, we too wrestle with prime numbers and show how their use in cryptography algorithms help to keep our money safe. Mathematicians have been fascinated by prime numbers for thousands of years, and it was back in 300 BC that Euclid came up with his fundamental theorem of arithmetic. Every positive integer greater than 1 can be expressed uniquely as a product of primes, apart from the rearrangement of terms.
For example, we could take the first few prime numbers, which are 2, 3 and 5, and we could multiply some of them together. For example, 2 times 2 times 3 times 5, and this is 60. Now, what the fundamental theorem of arithmetic tells us is that this was the only way we could get 60, except that we could have swapped some of the numbers around. So, for example, this is the same as 2 times 3 times 5 times 2, but apart from that, that's the only way that we can get 60.
After his lecture, Dr. Stevens and his colleagues take their exploration of primes a bit further.
So one of my students asked today why 1 wasn't a prime number. And it's an interesting question. I mean, it's almost by convention, isn't it? I mean, 1 is divisible only by 1 itself, and until the 19th century, I think people considered 1 to be a prime number.
The reason is to do with breaking down numbers. So we can break down numbers into prime numbers, and they're the smallest pieces we can break them into. And you can do that in essentially only one way. So, of course, you can swap the factors, but apart from that, there's only one way you can do it. But if 1 were a prime number, then you could put a 1 in there, or as many 1s as you like, and then there would be many different ways of factorising the same number into primes.
Wow, so that reminds me of atoms, because atoms are the building blocks of the universe, and this seems to be that primes are the building blocks of numbers.
So we have our building blocks, prime numbers, and there are infinitely many of them. And although they start small, they can build up to enormous things. So mathematicians started playing with them. They would multiply them together to create new numbers. So 3 times 5 gave 15, and 17 times 23 gave 391. But how, once you've got these new numbers like 15 or 391, could someone else come along and break them down into their prime factors? Well, there's still a little way to go yet before I can show you how prime numbers help keep your credit card details secure, but factorising is a key part to that solution.
We've seen that it's important to factorise numbers, and the simplest and most naive approach to factorising a number is to do trial division. So if I start with a modest number like 15, I'd start by trying to divide it by the prime numbers. So we see right away that 15 is not divisible by 2 because it's an odd number. The next prime to try is 3, and 15 is divisible by 3. And as soon as I find a divisor, I can divide by it, and I'll now be dealing with a smaller number, and my problem will be getting progressively easier. 5, happily, is a factor of itself and is a prime, so I've completed the factorisation now. 15 is 3 times 5. So this looks like a quite reasonable way to try and factorise numbers. But if I try a larger number...
If you choose 391.
391? But I can follow the same procedure. I can just run down the list of primes and see if I find a factor.
Mathematicians were finding that building numbers up from primes was a lot easier than breaking them back down into their prime factors.
The next number to try is 17. We see right away that 17 will go into 340, and 17 does go into 51.
While mathematicians in the blue corner were working on factorisations, the mathematicians in the red corner were searching for larger and larger prime numbers.
So one way that we can find prime numbers is using the sieve of Eratosthenes. So what we do here is we write out all the numbers up to some number. So here we've done it up to 100. And then essentially we start going through and crossing out the numbers which are not prime. Well, the number 1 is not a prime. Now the next number is always going to be a prime. So the 2 here is a prime. And now what we do is we cross off all the multiples of 2. So that's all the even numbers. So there they go. And now we look to the next number. So the next number is 3, which is also a prime now. And now we knock off all the multiples of 3. So those will be 9, 15, and so on. Now several of them have already gone, but there are the ones which haven't gone yet. Now the next number that's not been crossed out already is 5. So this is a prime. And all the multiples of 5 go, so they're down here. And now we look to the next number, which is 7. 7 is then prime. We cross out the multiples of 7. There are not so many of them left, 49, 77, 91. And actually now we've finished, because if we have a number which is no bigger than 100, then it has to have a prime divisor which is no bigger than its square root, in this case 10. And we've already coloured all the numbers up to 10. And so we know we finished, and all these remaining numbers are prime. And so we found all the primes up to 100.
Mathematicians were looking for larger and larger prime numbers. Apparently Gauss, who died in 1855, had sieved out all the prime numbers up to about 3 million. The gap between those looking for prime numbers and those trying to factorise numbers was getting bigger. And as the primes got bigger, factorising their products got harder.
Most of the largest known primes are Mersenne numbers. So these are numbers of the form 2 to the n minus 1. Now, the reason why these are usually the largest known primes is that there are special techniques that one can use to test a Mersenne number for primality. And many of these were developed by a mathematician called Lucas in the 19th century. So what he was able to show using his tests is that the 127th Mersenne number is prime. And here it is. As you can see, it's got 39 digits. It's a rather large number. He was also able to show that the 67th Mersenne number is not prime. But although he was able to show this, he didn't actually know how to factorise it.
Finding the factors of 2 to the power of 67 minus 1 was done in 1903 by a mathematician called Cole, and he did it by hand. And it's the last time a factorisation of this size was done using pen and paper. This was the largest Mersenne prime to be factorised before the advent of computers. And it's said it took Cole some 3 years of Sundays to do it. Now 3 years to factorise a number, that's a lot of effort to go to. Of course now we have computers, which makes finding new prime numbers and factorising numbers a whole lot easier.
One way to think of Cole's calculation is he computed 2 to the power of the 19th prime minus 1. If I compute 2 to the 67 minus 1, I see it's a large 21-digit number. And a modern computer will factorise that so quickly it feels instantaneous. Moving further along, and remember that number that was factorised there had 21 digits. If I ask for the 35th prime, it's 149. 2 to the power 149 minus 1 is a number with 45 digits, and factorising it, of course, is much more difficult. And there's a discernible pause, a second or two, while the computer arrives at these 2 large prime factors. Once again, it's a difficult number to factorise because it has no small prime factors. As I go through the primes, still concentrating on these special Mersenne numbers, 2 to the n minus 1, when I reach the 100th prime, that's 541. 2 to the power 541 minus 1 is a really very large number now, approximately 160 digits. If I try and get the computer to factorise it, we would really be expecting to go off and have a cup of tea before we get the answer. But it will come up with a factorisation certainly before lunchtime.
Maybe with computers the factorisers were catching up. Well, no, because computers were also used to calculate larger and larger prime numbers. The largest known prime number to date is a Mersenne prime, and it's 2 to the power of 43,112,609 minus 1. It's just short of 13 million digits long. Now imagine taking two really large prime numbers, multiplying them together, and then giving the product to somebody else to factorise. You're going to be waiting a long time for the answer. And it was this idea that Rivest, Shamir and Edelman used as part of their cryptography algorithm that we know as RSA. And those three academics from MIT earned millions from their creation. RSA forms the basis of almost all the security mechanisms now in use on the internet and has changed the way the world does business.
Okay, well the RSA function is based on clock arithmetic, or working in the integers modulo n. In RSA, you take n to be the product of two big prime numbers, p and q. And it turns out that for clock arithmetic, some arithmetical operations are easy whether you know the factorisation of n or not, and other operations are hard unless you know that factorisation. Okay, so to generate an RSA key, you generate two prime numbers. So let's call the first one p. So there it is, 1234, 1234, 1257. And q, 786, 786, 589. And then I generate a number n, which is p times q. There it is. And then I choose a number e, which I'm going to choose 2 to the 17 minus 1. And then I send n and e to Matthew. So what does Matthew do? He takes his credit card number and raises it to the power e modulo n to get some big number, and he'll send that number back to me. But what's hard is taking eth roots, doing the inverse operation. So it's hard for anybody unless they know the factorisation of n, and then it suddenly becomes easy. And that's the trapdoor function in RSA.
Now, a trapdoor function is something that's easy to compute in one direction, but is believed to be difficult to compute in the opposite direction. In other words, to find its inverse without special information. And the product of two large prime numbers is often used as part of a trapdoor function, because unless you know what the factors of the product are, then trying to work out the inverse of that trapdoor function is incredibly difficult. And of course, the larger the prime numbers, the harder the problem becomes. So that's how prime numbers can help keep your credit card details secure. It's going to take an enormous amount of effort to crack RSA, and that's a lot of effort to go to max up someone's credit card, particularly if they're on a teacher's salary. But we're not talking about one single credit card. Institutions like the Bank of England process many transactions. In a typical day, there are over 25 million credit card transactions worldwide. That equates to over $2,000 million floating around electronically. It's incredible. So maybe a mathematician in the blue corner will be able to devise an elegant way of factorising large numbers. Or a computer will be developed, powered by efficient and elegant algorithms, to work out those factors by trial division, crack the cryptography algorithms of today, and ultimately steal all our money. So I guess mathematicians in the red corner will continue to develop even more secure trapdoor functions to help keep your money secure.